the mole can be a lot of different things. There used to be like an old reality show called The Mole, and that's where this one here comes from. There's like a Swedish cartoon character that's been around for like 60 or 70 years. It's a mole. Moles on your skin. Uh, in chemistry, we're going to talk about this mole, though, which is a number. It's also referred to as Avogadro's number. 6.022 times 10 to the 23rd. You don't need to know all the decimal points, and actually 6.02 times 10 to the 23rd will be the number you use. So we'll just use it out to kind of 2 decimal places there, and then times 10 to the 23rd. So a mole is a quantity of something. So a mole is basically going to be 6.02 times 10 to the 23rd of whatever it is you're talking about. So if we say we have a mole of carbon atoms, it's 6.02 times 10 to the 23rd carbon atoms. If you have a mole of water molecules, that's 6.02 times 10 to the 23rd water molecules. If you have a mole of vitamin C molecules, it's 6.02 times 10 to the 23rd of those. So 6.02 times 10 to the 23rd is Avogadro's number, and it refers to kind of a known quantity of something. So this guy Avogadro said, okay, 6.02 times 10 to the 23rd of anything is going to be a mole. You could say you had a mole of M&Ms, right? And you would have 6.02 times 10 to the 23rd M&Ms. We use this as a conversion factor, which is what you can see down here on the bottom, right? So 1 mole is going to be 6.02 times 10 to the 23rd atoms, for instance, or it could be molecules. Remember the difference between atom and molecules. Like if you were talking about H2O molecules, so if we go up here and look at this one, right? H2O, we can say there's 1 molecule of H2O has 2 hydrogen atoms and 1 oxygen atom, right? The molecule is when everything comes together. All right, so if we were to look at this, how many molecules are contained in 5 moles of carbon dioxide? So we could say we're going to have 5.0 moles, and the abbreviation for moles is MOL, and a lot of times people will try to use shortcuts and abbreviation, and they'll use MOL to try to abbreviate molecules, which you can't do. We're going to have to write out molecules because moles and molecules, otherwise it's hard to know what unit you're working with. So if we want to know how many molecules you have, you would say that for every 1 mole of CO2, there's going to be 6.02 times 10 to the 23rd CO2 molecules. So see, I'm going to write the whole thing out there. And now I'll go ahead and write moles CO2 there. So now we can say we're going to cancel out the moles of CO2. We're going to cancel out the moles of CO2. And then this is going to equal, you would type on your calculator, 5 times 6.02. And on most calculators, the button for times 10 to the 23rd is that button that says EE, right? So that's going to be, on most calculators, you would type in 5 times 6.02, then use that EE button 23. And that EE button is times 10 to the, and then the exponent would be the 23rd. A lot of times, again, we talked about this a little bit in previous lectures, that's making sure you know how to properly enter the exponents on your calculator is going to be important here. You're going to end up with an answer that is 3.0 times 10 to the 24th CO2 molecules. Okay? So again, that would be molecules of CO2 in 5 moles. All right, so talking about some more conversions. So now, once we can know how many moles of something we have, a lot of times we want to know, well, how much does that mole weigh? So the formula weight of any molecule is going to be the sum of the atomic weights of all of the atoms in that molecule. So if we were to ask for the formula weight of nicotine, so nicotine is C10H14N2. So to figure out the formula weight, you would say, okay, so 1 carbon is going to be 12.01 AMUs, right? AMU is going to be, I'm coming from this number here, and it says 12.011. I'm just going to do them all to 2 decimal places. And we know we have 10 of them. So that's going to give us 120.1 AMUs from the carbons themselves. So the next one is going to be H. So H is going to be 1.01 AMU, and we have 14 of those. So for this one, we're going to have 1.01 times 14, which is going to give us 14.14 AMUs for the hydrogens. And then finally, nitrogen is going to be 14.01 AMUs. And we only have 2 of those, so that's going to add up to 28.02 AMUs. So that means that for nicotine altogether, we have to add those up. So 120.1 plus 14.14 plus 28.02 is going to add up to 148.4 AMU. All right, so that would be your formula weight for nicotine, 148.4. So a formula weight, whenever you hear the term formula weight, your units is always going to be in AMU, which is atomic mass units. Atomic mass units is kind of what we get from the periodic table. The formula weight in atomic mass units is also can be thought of as the number of grams in 1 mole of something. So the molar mass, which is the term you see here, is going to be the same thing, same as AMU. So it's going to be the same thing as the atomic mass unit. Atomic mass unit, the units are atomic mass units, and in molar mass, the unit is going to be grams per mole. So here our units are going to be grams per mole. So in this case, if you look down here in this box, it says carbon's atomic weight is 12.01 AMUs. You can also say that carbon has a molar mass of 12.01 gram per mole, right? So in other words, 1 mole of carbon would weigh 12.01 grams. So going back to the previous slide, we could also say that the molar mass of nicotine, molar mass of nicotine would be 148.4 grams per mole. Okay, so AMU and grams per mole are 2 ways you can look at this. The formula weight is going to be usually given in AMUs. The molar mass is in grams per mole. The molar mass is the one you're going to be using a lot more because it's a conversion factor. It will tell you how many grams of something you have per mole. So we can use this. If we know the number of moles, we can figure out the grams. If we know how many grams of something we have, we can also figure out how many moles we have. So this term down here is going to be one that we're going to use quite often, specifically in terms of using it as a conversion factor. Okay, so if you had a question like this, how many moles are present in 100 grams of aspirin? And in this case, I went ahead and gave you the molar mass, right? So I told you that aspirin is C9H8O4 and it has a molar mass of 180.2 grams per mole. If I told you that was the formula for aspirin, you should be able to calculate this number yourself. Sometimes I'll do that on a test. Other times you'll have to be able to calculate it yourself. Just make sure you know how to figure out the molar mass from the chemical formula. So in this case, though, since it's already given to us, we can do the conversion. So we know our conversion factor is going to be this 180.2 grams per mole, which means that if we know how many grams we have, we should be able to use the conversion factor to convert it to moles. So I'm going to start with what I'm given, the number that's not the conversion factor. right? 100 grams of aspirin. And I want to convert that to moles. All right, so I know that because I have grams of aspirin that I start with here, I need to have grams down here on the bottom. So I need to have grams of aspirin on the bottom. And I know that there are 180.2 grams of aspirin for every 1 mole of aspirin. And then if I go through and do the math on this, I can see that first off, the grams of aspirin are going to cancel out with grams of aspirin. And then I'm going to do 100 divided by 180.2. And I should write this at 3 significant figures because, right, 100 with a decimal point is 3 significant figures. So that's going to be 0.555 moles of aspirin. All right, so that would be converting grams to moles. Now, you could also convert, if you were given moles, you could convert to grams. The only difference then is you would flip your conversion factor, again, making sure that we're canceling out units. Whatever's on the top has to go on the bottom next to it. Okay, so in terms of more conversions with moles, a balanced chemical equation, right? So we talked in the first part of the chapter about balancing a chemical equation. So the balancing a chemical equation is important because of the law of conservation of mass, right? It tells us that matter can't be created or destroyed in a chemical reaction. Once we have that balanced chemical reaction, the coefficients that we have, so in this case, the 1, and the 2. And again, usually you wouldn't write 1s as coefficients, but they're there kind of for illustration points here. Those tell us that you could have 1 molecule of N2 reacting with 1 molecule of O2 to form 2 molecules of NO. Now, another way to say that would be to say that you have 1 mole of N2 reacting with 1 mole of O2 to form 2 moles of NO. So moles and molecule are not the same thing. So the one thing I want to clarify is that even though this has 1 mole of N2 here and 1 molecule of N2 here, those are not the same thing. Remember, 1 mole of N2 is actually 6.02 times 10 to the 23rd molecules. But what this is saying is that the ratio is the same. If you had 6.02 times 10 to the 23rd molecules of N2, that would react with 6.02 times 10 to the 23rd molecules of O2, and you would form 2 times 6.02 times 10 to the 23rd molecules of NO. Another way to say that is 1 mole reacts with 1 mole to form 2 moles. All right? So those coefficients allow us to come up with more conversion factors to be able to convert from one molecule to another. So, in other words, we can say that these mole ratios, looking at this line here, we can say that for every 1 mole of N2, there's going to be 1 mole of O2 that's used. We can say that for every 1 mole of N2 that reacts, 2 moles of NO are going to be formed. Again, that's because this coefficient here is 1, and this one over here is 2. For every 1 mole of O2 that reacts, 2 moles of NO are going to be formed. All right? So these mole ratios allow you to convert from moles of one compound to moles of another. So you're going to see problems where it gives you like, okay, if you have 10 grams of O2, how many grams of NO are you going to be able to form? Well, the only way you can convert from one molecule to another molecule is to figure out their relationship in moles. You have to convert it from grams to moles before you're able to do it. So these conversion factors, like you're looking at down here, always have to be done in moles. So it's always going to be a mole to mole conversion whenever you're converting from one molecule like N2 or O2 to another molecule like NO. Okay, so here's a problem, right? So in the reaction below, and I'm telling you it's unbalanced, so the first thing we're going to want to do is balance the reaction. How many moles of carbon monoxide, CO, are produced from 3.5 moles of ethane, which is C2H6. All right, so first things first is we want to make sure we have a balanced chemical reaction. So if we look at this one, we can see we have 2 carbons over here. So let's go ahead and write down kind of what we have. C, H, and O. And we have, I'll draw my squiggle here. So we have 2 carbons on the reactant side, and we only have 1 carbon in the product side. We have 6 hydrogens in reactants, and we only have 2 over here in the products. And we have 2 oxygens in the reactants, and we have 2 oxygens in the products. So anytime you see, this is called a combustion reaction. Anytime you see reactions with carbon like this, it's a good idea to start with your carbons. You could also start with your hydrogens here, but it's going to be, in this case, it's going to be easier to start with your carbons. And what we can see is if you have 2 over here and 1 over here, the first thing we know is we need to put a 2 over there, right? So now we've kind of changed our numbers of carbons and our number of oxygens. So now we're going to have 2 carbons over here, and we're going to have 3 oxygens. Next up, we're going to need more hydrogens on the product side, right? So we're going to need a 3 there. So that's going to get us to, now we're going to change the number of hydrogens is going to be 6. And now oxygens is we're going to have 3 over here, and we're going to have 3 with the water and 2 with the carbon monoxide, right? So 6 there, and we're going to have 5 of oxygen. So again, this is called a combustion reaction. Whenever you have a carbon containing something reacting with oxygen to form CO or CO2. This is actually called an incomplete combustion. We'll get to this in chapter 10. If you always balance your carbons first, then your hydrogens, then you go to the oxygen, it'll always kind of work out this way. And what we can see here is that we need to have 2 oxygens on the left and 5 on the right. So in a perfect world, we could write 2.5 here, right, as our coefficient. And we could say 2.5, we could say we have 2.5 here times 2, right, the coefficient times the subscript would give us 5. But we can't write fractions or decimals as our coefficients. However, if you can see that and understand that it would be 2.5, the easy rule of thumb after that is going to be to go ahead and multiply all of your coefficients by 2. So basically, we're going to put a 2 in front of this one. Instead of 2.5, we're going to multiply that by 2, and that would give us 5. Instead of 2 there, that's going to give us 4. Instead of 3 there, that's going to give us 6. And that's going to end up getting us to a balanced chemical formula where we're going to have 4 carbons, we're going to have 12 and 10, and we're going to have 4. For hydrogens, it's going to be 6 times 2 to give us 12. And for oxygens, it's going to be 4 COs, so that's going to be 4 oxygens there, and then 6 H2Os, so 6 more oxygens there, which is going to give us 10. Now, if you have trouble figuring out this, this 2.5 idea here, if you keep adding, changing coefficients, you're going to get there. All I had to do is kind of, right, I started off with a 1 here, I changed it to a 2, and everything worked out. But that's what you would have had to do, because what would have happened here, if you look at the red numbers, if I had 2 and 5, right, if I try to put a 3 in front of the oxygen, that would have taken it to 6. And then I would have had to come back over here to try to add a more oxygen. And as soon as I try to add a more oxygen, then I'm going to be changing numbers of carbons or hydrogen. So eventually I would have gotten to those blue numbers if I didn't have the shortcut. But I wanted to show you that kind of shortcut because I think it's helpful. Okay, so that was the balancing the chemical equation part. Now we still need to figure out how many moles of CO are produced from 3.5 moles of C2H6. And this part of the problem, we're going to use our balanced chemical reaction to come up with a conversion factor to go from 3.5 moles of C2H6 to figure out how many moles of carbon monoxide, or CO, we have. So now I need a conversion factor. So I know I need to get rid of moles of C2H6, and I want to convert it to moles of CO. And to do that, I'm going to use the balanced chemical equation. So I know I'm going to have 4 moles of CO, and I'm going to have 2 moles of C2H6. So I'm going to have 4 moles of CO, 2 moles of C2H6. That's going to be a total of 7 moles of CO. And that would be our final answer. So again, moles, start with moles here, get rid of moles of C2H6 and convert it to moles of CO. Alright, so again, balancing your chemical equation is always going to be something you need to start with in order to be able to use these mole-to-mole conversions. Alright, so we're kind of building up here. And now this slide here kind of shows you how you would go from grams of reactants to grams of product. So in order to do a problem like this, it takes 3 different conversion factors. So 2 slides ago, we did grams of reactant to moles of reactant. Okay, that was in that aspirin example that we did. When we had 100 grams of aspirin, we calculated how many moles of aspirin it was. The problem we just did converted moles of one thing to moles of another thing. Moles of reactant to moles of product. Right, and that's how we use a mole-to-mole conversion factor. And then the last step to this is going from moles of product to grams of product, which is basically the same thing as step 1 over here, except that it's going in the other direction. So again, 3 consecutive conversions that will get you from grams of reactant to grams of product. So let's look at an example here. So how many grams of NH3, which is ammonia, can be formed from 15 grams of N2? Alright, so I'm going to start with 15 grams of N2, because I know that's what I have to start with here. And in order for me to get from N2 to NH3, I need to be able to do a mole-to-mole conversion. The problem is that what I'm starting with here isn't in moles, it's in grams. So what I need to do is figure out how many grams per mole I have for N2. So in order to do that, we need to go to the periodic table. And if you look at the periodic table, nitrogen is 14.01 AMUs, or grams per mole. So N2 is going to be 28.02. So that means I can come over here and use that as my conversion factor, and I can say that there are 28.02 grams of N2 per 1 mole of N2. And now I've went from grams of N2, that canceled out, and if I did the math there, I would know how many moles of N2 I had. It would be about half of a mole. I like to just continue doing my problems one step at a time. You could do equal here and do the math if you want. I just like to continue my conversions. So now I know how many moles of N2 I have. Right, so I know how many moles of N2 I have, but now I want to convert N2 over to NH3. And I can see that based on the balanced chemical equation here, for every 1 mole of N2 I have, I'm going to have 2 moles of NH3. So I can use that. For every 1 mole of N2 that I have, I'm going to have 2 moles of NH3. Once again, I can cancel out my units. Moles of N2 are gone. So now I know how many moles of NH3 I have. So now I want to know how many grams of NH3 that I have. In order to do this, I need to know the molar mass of NH3. So hydrogen is going to be 1.01 AMU, or grams per mole. So that means for NH3, it's going to be 14.01 plus 1.01 plus 1.01 plus 1.01. That's going to give me the 17.04 gram per mole. So I can come over here and in one more step, I can say that for every 1 mole of NH3, I'm going to have 17.04 grams of NH3. I've almost run out of room here, but what you can see, moles of NH3 cancels with moles of NH3. So I'm going to go ahead and say that's going to be kind of your final expression. So now we have to go through and type in the math on your calculator. So what you're going to do is you're going to say 15 and then divided by 28.02 because that's on the bottom, times 2 because it's on the top, and then times 17.04. And that is going to give you an answer that's going to be 18.244 is what my calculator says. In this case, though, we only would need 2 significant figures because the number is 2. So I really don't even need the point down there that I wrote. So let's get rid of it. So 18 grams of NH3. That would be our final answer. So from 15 grams of N2, we can form 18 grams of NH3. And again, this problem is going to be similar to many that you see. The 3 steps, going from grams to moles, then going from moles of one thing to moles of another. We went from moles of N2 to moles of NH3. And then from moles back to grams, so moles of NH3 to grams of NH3. So those are going to be your 3 steps in these problems like this.